So if you have your unit circle, I want you to turn it over. We're going to practice this for just a second, okay? So on a test or a quiz, if you want to recreate the unit circle, you can in its quadrant, because I really want you to practice going, using reference angles. Let's see if we can come up with the first quadrant. So you could draw the first quadrant, and we want to write down our radian and degree measures for all 5 of these angles. All 5 of them. So just starting with the degrees, we would start with 0. What's next?
30.
Okay. 45, 60, that's right. And then 90. Now let's change those to radian values. They're all just fractions, aren't or
Pi over 2, right?
0. Well, let's go in order. How about that? So we're going to go 0. Pi over 6 is the smallest one right there. Then we have pi over 4, pi over 3, and then pi over 2. All right, now let's do the ordered pairs. Starting at 0, on our unit circle, we would have 1, 0, right? Okay, and then we can come up here and we can say, okay, that's 0, 1 at the very top. These are the 3 here that usually get a little bit confusing. And it's really only the 30 and the 60 that get confusing. So let's do 45. Who remembers what pi over 4 is? Yes, sir? Square root of 2 over 2. Square root of 2 over 2. That's right. Okay? So those are usually the 3 of these 5 angles. Those are usually the ones people can get them down pretty easily. How about pi over 6? Remember what the ordered pair would be for pi over 6? Very good. Square root of 3 over 2 for the x coordinate, and then 1/2 for the y. And then it's the reverse of that, right, when we deal with 60 degrees. 1/2 square root of 3 over 2. That's right. So that's the first quadrant, right? So when you get on a test, by all means, write that at the top of your paper, okay? And we use this, right? We're using this unit circle to help us identify the 6 trig function values all the way around the circle. So as a refresher, right, if I wanted to know what the sine of pi over 6 is, what would you tell me? Yeah, did I say sine of pi over 6? 1/2, right? Sine of pi over 6 is 1/2. All right. How about cosine of 90? Cosine is going to be your x value, right? Sine is going to be y. So cosine is your x, sine is your y. What about the tangent of pi over 4? It'd be 1. Because any number divided by self is always 1, right? So that one is like that. Okay, so the first quadrant is kind of handy-dandy to learn. So now I'm going to give you a technique. If you were stayed with me after class yesterday, I was kind of starting to explain this. This is just a memorization technique, I would say, right? Because you're supposed to be able to memorize all of these things. So I'm going to walk you through one technique that I found that I love. If you don't like it, it's fine with me. Just don't ever use it again. All right? So I'm going to walk you through how you set this up. So this is called the trig hand something, right? All right. So like I said yesterday, you have to be careful if you ever Google that. That right there. Everybody take your left hand, right? Now your left hand, when you look at it, in front of you with your thumb pointed to the top and your pinky pointing over to the right, represents 5 angles. These 5 angles right here is what your hand is representing, the first quadrant, all right? Your pinky represents 0 degrees, your thumb represents 90 degrees, and the fingers in between represent 30, 45, and 60, okay? So that's the first quadrant. Now the setup on this says that my digits, my fingers, are always going to be in the numerator, and they're always under a square root symbol, okay? Just remember that. Fingers are the numerator under a square root symbol. The palm of your hand is always a 2. Under a radical is my fingers. The palm is always a 2, okay? Now I want everybody to fold their ring finger down. Fold your ring finger down. I just chose 30 degrees, right? Yeah? Okay, so what this says is that my finger under the fold represents sine. My fingers above the fold represent cosine. So this says that the sine of 30 is going to be 1/2. Numerator, denominator. Isn't that beautiful? Right? 1 is under the radical sign or square root sign. Square root of 1 is always 1. Cosine is above the fold. Square root of 3 over 2. Is that what's up there? Square root of 3 over 2. Okay, this gets better. All right, what's tangent? Sine over cosine? Sine over cosine. 1 over the square root of 3. Okay? What about the reciprocal of sine? That would be cosecant, right? Cosecant would be 2 over 1. You go in the opposite direction. 2 over 1. Secant of sine, secant of pi over 6. That's the reciprocal of cosine, right? It would be 2 over the square root of 3. All right? Cotangent of pi over 6. Go in the opposite direction. It would be cosine over sine. Square root of 3 over 1. You get it all right here. If you watch me do this, this is what I'm doing with my hand because it's a memory. It's just something that I've chosen to do, right? That's how I chose to memorize them.
Are you getting 3 from what, like 3 fingers?
Yeah, I called them digits, but people always look at me strangely. Because technically those are your fingers, right? Plus your thumb. It's 3 digits. Let's practice another one, okay? Let's do pi over 4. That's your middle finger, right? So if I fold down pi over 4, if I fold down 45 degrees, the sine, I always have to hold it because it doesn't want to stay folded, right? So sine of 45 is going to be the square root of 2, because it's under a square root symbol, over 2, right? Square root of 2 over 2, and then cosine is above the fold, square root of 2 over 2. Okay? Tangent would be the square root of 2 divided by the square root of 2, right? Any number divided by itself is always going to be 1. See how that's working there? Okay? You can do the quadrantals also. They work. I don't usually do them. I'll usually just make the plus sign and write the ordered pairs, and I can go on from there. But I will use this. This is so much easier for me personally when I'm trying to memorize these because I have the first quadrant here, and I can use reference angles to go around, right? And I also don't usually, because I know, because I've practiced it, and I know which one represents sine and which one represents cosine, so I don't generally mix up anymore these two if I'm thinking clearly, okay? I don't usually mix those up. Okay, so let's practice that, all right? All right. Let's look at these 3 angles here. Now, I don't want you to answer them out loud just yet, all right? We're going to think through this process right here. And we're going to use reference angles to be able to talk about these 3 angles, right? Or these function values, I should say. Okay, so if I wanted to know what the sine of 7 pi over 6 is, first of all, I'm going to think 2 things. What's the reference angle for 7 pi over 6? Pi over 6, okay, I'm getting thinking on here, right? What quadrant is 7 pi over 6 in? Third quadrant, so sine has to be negative, right? So now I know, because I just folded down pi over 6 in my hand, that the sine of 7 pi over 6 is going to be negative 1/2. Are we right? You can flip your unit circle over and we can check. Sure enough, it is -1/2. All right? If you flipped it over, now flip it back, okay? Because we're practicing. So we know that this is in quadrant 3, that the reference angle was pi/6, so the answer was -1/2. All right, let's look at cosine of -4 pi/3. First of all, what's the reference angle for -4 pi/3?
Negative pi over 3.
Just pi/3. You're right, it's an acute angle, but we'll just keep it as the one that's coming from the first quadrant. So, correct, pi/3 would be our reference angle. So in my brain, I'm folding down my pointer finger here. What quadrant is -4 pi/3 in? 2. It's in 2 because we rotate negatively, remember? So we go a little bit past halfway around the circle. So we are in quadrant 2. Our reference angle is pi/3. So I know that cosine is negative in quadrant 2. So the answer here would be 1/2 again, wouldn't it? 1/2. -1/2, I should say. Okay, we good with that? How about cosecant of 11 pi/6? Now, what's the reference angle? Pi/6, very good. So the reference angle is pi/6. What quadrant am I in at 11 pi/6?
4.
Right, because all the way around is 12. I back up, I'm in the 4th quadrant. So 4th quadrant, pi/6. What is the reciprocal of cosecant? Sine. So opposite letter, sine. So I know that sine of this angle is 1/2. So cosecant going the opposite direction has to be 2/1 or -2 because we're in the 4th quadrant. Do you see how I'm putting all of those pieces together? Reference angle, what quadrant is it in? And if need be, I'm going to use the reciprocal to be able to figure that part out, right? So I've got a couple of steps that I'm doing, but that's the process that I'm going through. So it's a little long at first, but you'll get faster at it the more times you practice at it. Okay? You can be able to do that? Okay, because you'll have a quiz over this material on Monday of next week, right?
Wait, this upcoming Monday?
Yep, that Monday, yep. Okay, I'm going to give you an opportunity to practice these things again in just a minute, so we'll practice. That's kind of the point of our stuff that we're doing today. But I do want you all to get your calculators out for just a second. Understand that when we ask for exact circular values, exact answers, anytime I'm talking about exact, I'm talking about not a calculator answer, right? Okay, so you're going to have to give me those ones that involve the radicals like we were just describing. So I want to find the function values for both sine and secant of these angles that you see here. Now, I have told you that it is radians, right? But there's no degree symbol that's listed on either of these two measurements, so it's implied that these are radians. If you're not told, you just should try to assume that it is radian measure if it's no degree is found. So when you go on your calculators, you're going to go to the mode button, scroll down until you click radians, and change your calculator from degree mode, if it was in degree mode, over to radian mode. That's the only thing that I want to point out on this one. Now let's see if we can find these angle measurements. We remember, because it's pretty easy, if you get one of the sine, cosine, or tangents, then you just plug and chug right there, right? So let's say to 4 decimal places.
0.731.
Okay, does everybody get 0.7314 for function values? Okay, now there is no secant button on your calculator, and I want to know what is the secant of this angle. So we use the reciprocal identity to say that secant is the reciprocal of cosine. So 1 over the cosine of that angle, 2.8440, rounded to 4 decimal places.
Negative 1.44.
Is it 0460?
Yes.
Did I round it right?
Rounded to.
Okay, I couldn't remember if I rounded it right. Now, and think back, does that make sense? We know that 2.8 radians, right, would put us approximately where? What quadrant would I be in at 2.8 radians? Quadrant 2, right? Because 3.14 radians is pi, isn't it? So I haven't quite made it around a pi, but I'm past pi over 2. So second quadrant, cosine is negative in the second quadrant, so that makes sense for that function value to be negative right there. It's just a way for you to mentally check whether or not that is logical. All right, so that's just a reminder of your function values. Now, I will say that you just need to pay attention to this concept whenever I give it to you on a test. I have students who miss these all the time because they just have their calculator in the wrong mode. All right, so just pay attention to what when you're using radians and when you're using degrees. All right, the last thing that I want to practice together before I have you all do a little bit of extra classwork is what we were leaving off with last time. And so I want to come back and I want to revisit this using our new hand trick, right? If you choose to. Now we know, because we were talking about this last time, we know that the sine of any angle, is going to produce 2 positive values and 2 negative values, right? The sine of any angle produces 2 positive values and 2 negative values. Because sine is positive in the first and second quadrant, and it's negative in the third and the fourth quadrant. So whatever angles land in the first and second quadrant give me back a sine value that's positive versus third and fourth quadrants, which give me negative values. So you have 4 answers for sine. 2 of them will be positive and 2 will be negative. And we know from looking at the unit circle that they're all the same number, right? They would all be the same function value. The sign, positive versus negative, is what's changing as you move around. So, if I wanted to know what angle, when I do take the sine of it, is going to give me 1/2. So I'm going to take my hand and I'm going to fold down so that the number below the fold is going to be a 1, because 2 is always my palm. Now I know that 30 degrees or pi over 6 is the angle that gives me 1/2 when I take the sine of it, right? But we're going to restrict that, and we're going to say, so this angle, this finger I have folded down is representing 30 degrees or pi over 6. The restriction is given to me in radians, so I need to give my, I need to be considering my answer needs to come back in radians. So this is restricting where I'm looking. I'm only going to look for angles that are in which quadrant?
2.
Second quadrant, right? I'm between pi over 2 and pi. I'm between pi over 2 and pi. So what angle, if pi over 6 is the reference angle, what does that angle become in the second quadrant? Positive. So I'm going to go all the way around to 6, 6, and I'm going to back up to be pi 1. I'm going to back up 1, and I'll be at 5 pi over 6. 5 pi over 6, or what would that be, 150?
150.
Uh-huh. Okay, do we understand how I'm focusing in, I'm laser focused in on only quadrant number 2 to get that answer? All right? Let's try that again. So in this next one, I want to know what angle, when I take the tangent of it, I get a -1. So let's just kind of think reference angles here. What angle, when I take the tangent of it, is going to give me the number 1? 45s always give me a 1 for tangent and cotangent. Now, I'm going to pick on you because it's not 45, it's going to be a pi over 4, right? So the fourths are always that. What quadrant will I be in if I am restricting it from 3 pi over 2 to 2 pi? Fourth quadrant, right? So now I have a reference angle of pi over 4, but I need to place that angle in the fourth quadrant. What angle are we looking at? In radians. So go all the way around to 8 pi and back up 1. I'm at 7 pi over 4, which is 315. Okay? 315. So here we said this one was the second quadrant, 5 pi over 6. Here, this is the fourth quadrant. We're at 7 pi over 4. Now look at that last one. I want to know what angle when I take the cosine of it, I get this. Can you make your fingers do this?
No.
Okay, so this is a calculator issue. All right, this is a calculator issue.
Quadrant 1 though, right?
Yes, and how did you know we were going to restrict it to quadrant 1?
Because of the restrictions at 0 pi over 2.
Exactly. So we are going to only look for angles that are going to fall in the first quadrant. Now for our calculator, this is where we actually are going to use the inverse function. So if you look at your calculator, you'll see above the cosine button, something that looks like that, cosine to the -1, is the mathematical notation for the inverse. So I'm looking for the inverse of 0.7826. Push those buttons for me. We're already in radians, so we're going to get back an answer that's in radians. And what you get back is what, 0.6720? Okay, now what I found is that the cosine of 0.6720, so 0.6720 is an angle. All right, so when I find the inverse, I'm finding the angle. When I just do cosine of the angle, I find the function value. Those get confusing sometimes. So the inverse gives me the angle versus us taking the cosine of the angle to get the function value. Okay? We do a whole lot. Well, I think we'll do next week we'll be talking specifically about inverse functions. All right? So that's what we're looking at here, and that's using our calculator. So there's a lot of mental math, maybe some imagery that you're trying to think of, right? When we're trying to place these angles around the unit circle, there's a lot that's going into it, but it's all kind of mental, and it's really just going to get easier with you practicing, okay? I found that it does help me if I'm trying to make notes to myself, like, you know, maybe I'm going to draw a picture, and I'm going to put an angle over here in between pi over 2 and pi. That's a mental note to me that I'm talking about quadrant 2, and I can go on from there, right? Generally sketching something as minuscule as that is helpful. And then, like I said, although the hand trick is very, very, I like using it, the other thing that I found, if I'm just kind of giving hints on memorization. You can do whatever you want, but I found that just to go around here and write a couple of these, even if I just write those, and I can fill it in, it just depends on how much time I'm taking, right? That takes me less time to write this right here than it does to consistently make a mistake on my quadrantals, which I found that I was doing, okay? So rather than keep making that mistake, I decided to just do something else, change what was wrong, right? Do something different. Okay. You feeling a little bit more comfortable in what you're looking at now? All right, so I want you to take a little bit of time. This is where you're going to get to practice this. And we're going to take a little bit of time to work on, let's see, how much can I spit on there? Let's just do the top 10, 1 through 10. All right, now, try to only use the first quadrant, right? Try to use the hand trick if that's the one you want. I can come around and help you with it again. But I want you to answer these questions. Check with your neighbor if you need. But take a little bit of time to try to work on these. We'll take about 10 minutes. Right, there's the answers for 1 through 6. Hopefully I didn't make any mistakes. If I did, just point it out to me. Because I make mistakes on them as well. Nope, you're right.
It's 2?
It should be 2. Remember. Right? Can I move it up? Am I right? Okay. Can we go? Keep going? Almost?
Almost.
We went through 10, right? And then we changed and went through the rest? I got -1 up there.
Yeah, I was trying to see what my answers were.
Okay. And then 19 through 23, right? 19 through 23. All right. Are these right? Did I get them all right? Right? If you agree with me, then I think that we're right, right? If our answers aren't the same, then ask, because I could have gotten it wrong. All right, so a little more practice on this, because that's what it takes. Practice, practice, practice. Okay? Do we have a question on it or anything? All right. So what I'm going to do is I'm going to come around and I'm going to hand you a set of problems. All right? Do not write on my piece of paper. Write on your own piece of paper and write down what numbers these are. Because we have to exercise in my class, don't we? I make you exercise, don't I? So what you're going to do is you're going to answer these 4 problems, and then you're going to get up, and you have to physically get up and go to the other side of the room and find somebody else who has the exact same set of numbers as you, and compare your answers. Because we think if we've both got the same set of numbers, then you should both be right.
Is this the same thing we were doing on 19 to 23?
I'm going to put the instructions up there, but I think it is. Did I give you one yet? Have I done this right? Just a second, and I'll put the instructions up on the board. Right? Did everybody get a set of numbers? Okay. So you have the numbers anywhere between 19 and 34. You're finding the exact value without your calculator.
Oh, so it's the same thing.
Same thing we were doing before. And we're just repracticing those problems or similar problems. But you need to own. Okay. Did y'all get them? Did you find your people? You found your people, and did you get them right? If you didn't, do you know where you're? Errors came in?
So where I messed up was I did 6.6. So I was moving it that way, so I did time. So it just got
All right, when you're done, bring your pieces of paper up here and put them on my desk. And then go sit back down. I got another one for you. Just put them up here and pile them up. Practice, practice.
The highlighted one is the one we did.
No, it's just that. No, just no. Want to come and visit with me and talk it out with me, that's absolutely, I would encourage you to do that. Okay, let's take a minute. Since it's the end of the week, I told you that I would be able to come back and revisit our angles, arc length, linear angles, linear speed, and angular speed. Now, if you've already done this, you were able to successfully do the Desmos activity, great. This will just be a review for you. If not, then, whatever. All right, so I just kind of want to go over one more time. When we think of arc length, right, when we think of the length of the arc, it's a measurement. And if we have this circle here with a central angle, the circle has a radius of r with a central angle, then the measure along the outside right there is the arc length. We define arc length as S is equal to r theta. And the only thing you have to remember that's special about all of these radian formulas that we're talking about here is that theta has to be in radian measures, so you have to convert it. Okay, I think most everybody knows how to do this, but let's just practice a couple of these examples together and maybe walk through it. If the first example, so you want to make sure you've got something to write on if you don't already. The first thing that we're going to look at is we have a radius of 3 meters. We have an angle of 150, and I want to know what is the arc length. So if I'm plug and chug into the formula, I've got 3 meters times, that's the radius, times theta, which is 150 degrees. And I've got to multiply 150 degrees by pi over 180. That's right. So pi over 180. Now, I want you all to recognize what I'm doing there as far as setting this up. When you get just, lickety-split, dandy, and you don't have to do all of this notation, don't do it. But for right now, maybe you need to take the time to do this. I'm setting this up as a unit conversion so I can clearly identify what's going on here, right? My degrees are going to cancel out. That leaves me with pi in the numerator. That means that I have my angle now in the correct form. And then I would just multiply the 3 times the 150 times 1 pi and divide it by 180, right? It's just a multiplication divided by and division, which are on the same as far as operations are concerned. So everybody in your calculator, put those numbers in, right? 3 times 150 times pi divided by 180. Into 2 decimal places, tell me what you get.
7.853 meters.
All right, so to 2 decimal places, we should get 7.85 meters. Now, one of the things that's a little bit tricky when you're looking at these things is I converted my angle into radians, so what happened to radians if we're thinking about units, right? So I don't have I don't have anything good to tell you except that radians is not really a unit, somewhat unitless. There's some different contradictory ways to explain it, but I like to think of radians as just, sometimes I'll put it in there just so that I can identify that I have changed my angle into the right mode. Okay? All right, because ultimately we don't write meters and radians together here. We would just say that this is, the length of the arc would be 7.85 meters. Now I'm going to really screw you up because when I come over here, right, when I look at this one right here, this next example that I have, it says that the radius is 14 feet, the arc length is 8 feet, and so I want to know what is theta. So if the formula is the arc length is equal to r theta, therefore theta has to be S divided by R, right? So if I put 8 feet, 8 feet in the numerator divided by the 14 feet in the denominator, I am going to just leave this as a decimal. Well, I found my feet units canceled, didn't they? But I'm talking about theta. I haven't done any conversions to get this thing out of radians and into degrees. So by default, the formula is going to give me theta in radians, unless I do something special, right, to put it back into degrees. So I would say that this would be 0.57 radians. Do you understand that? That the formula by default gave me radians, gave me an angle in radians. All right. Let's look at another example here. This is a classic example about latitude. Yeah, because that's all I wanted to know. What was the angle? And unless I said, give me the angle back in degrees, right? Now, we'll see in a minute, Riley, when we look at the others, like if I'm using this, I need it to be something different. All right, so here we have Pittsburgh, Pennsylvania, which is approximately due north of Panama City, Panama. The latitude, in other words, the angular distance as we go north and south of Pittsburgh is 40 degrees north, while Panama City is 9 degrees north. We want to figure out how far the two cities are from each other. All right, that's what we're trying to figure out. And we know that the radius, or given that the radius of the Earth is 6,400 kilometers. So we know the Earth is round, right? We all know that. And here we've got Pittsburgh up here. And here we have Panama City down here. We would have a center to our round Earth. So in other words, the Earth has a radius of 6,400 kilometers. And the radius to Pittsburgh and the radius to Panama City would be the same, right? So I can create now basically a similar problem as we were just working. The thing that I don't know is this angle that separates Pittsburgh from Pennsylvania. I do know that Pittsburgh is at 40 degrees north. Panama City is at 9 degrees. I don't know if that's what I said before. 9 degrees north. So the difference between those two angles, 40 minus 9, is 31 degrees. So there's a 31 degrees latitudinally, I think, or longitudinally. I can't really remember. Latitudinally, right? There's a 31 degree difference between the two cities on the surface of the Earth. So if I know that the radius is 6,400 kilometers, I know theta is 31 degrees, then I can just use the arc length formula to find out the distance. So S is equal to 6,400 kilometers times 31 degrees, but you have to change that into radian measure. So times pi over 180. Remember, my degrees are going to cancel out. It's going to give me kilometers. So rounding to the nearest whole number, what do you find? What is the distance between Panama and Pittsburgh? 3,463 kilometers. All right, so a couple of examples, a couple of more examples on arc length. All right. Now let's move on into, everybody have that written down? Everybody good with that? Almost good with that? I'm just going to move it up just a little bit. Remember, the formulas for, they're down here. Remember the formulas for linear and angular speed. So the linear speed, which is a velocity along a straight line, right, or along the edge, let's say, right? Linear speed is just velocity. Linear speed is defined as the arc length over time. Can I move it up now, Riley? We good? All right. So linear speed is defined as the arc length over time. Now the derivation, you can see that in the side over there. The derivation comes in that we've already defined arc length S as r theta. So if I substitute r theta for the numerator, it's still over time because velocity is a measurement with respect to time. Okay, and then I'm going to jump down to the bottom one for just a second because in the bottom one, the angular speed, so it's how fast the angle is changing with respect to time. So that's going to be theta over time. Now how that affects the linear speed is that if I go back up there and look for just a second, if theta over time is omega, is w, then I can rewrite linear speed to also be represented as rw. So depending on where you're at in this can depend on which formula you would be using. All right? You see where all of those things are coming from? Okay, so we have linear speed and we have angular speed. Now the other thing that you have to consider here, and of course because these are radian formulas, our angle that we're looking at must always be converted into radian measure. Okay, you don't go out and generally measure things in the real world in radians, you measure in degrees, right? But if you're going to use these formulas, you got to convert that into radians. But the other thing you want to consider that you have to understand here is that one revolution around the circle is the same thing as 2 pi radians. One revolution around is 2 pi, right? Okay, per minute. Okay, I think that should be per minute. So let's look at this example that I obviously needed to spell check. Okay. We have a 7¼ inch circular power saw blade that rotates 5,200 revolutions per minute. And I want to find the angular speed of the blade in radians per minute is what that says up there, right? So I'm looking for angular speed, and I'm looking for it in radians per minute. So the first thing that I'm going to do is I'm going to write down, this is for question number A. What do I know? Well, I know that this blade is going to rotate at 5,200 revolutions per minute. That's right. Okay. In order to determine omega, I've got to know what theta is with respect to time. Well, theta has to be in radians. It can't be in respect to revolutions. But I know that 5,200 revolutions, and I'm just writing this in the unit form just so you can see what I'm doing, times 2 pi radians over 1 revolution gets rid of the revolutions and puts theta, takes it out of revolutions and puts it in terms of radians, and I would now have, what would that be, 10,400 pi radians. Now I'm not going to round at this point. I'm not going to find the decimal value at this point. You're going to end up with a rounding error unless you go back and keep using. You can go back up on your calculators, but anyway. So now, if I come back over here, I know that this is 10,400 pi radians per 1 minute because I was dealing with revolutions per minute, okay? Does that make sense? All right. Now the decimal value of this is going to be 32,672.6 radians per minute. Okay, radians per minute. Are there questions on that so far? I'm trying to show you my units that I'm using here. So the second part of this question says, I want to now know what the linear speed is in feet per minute. So velocity is equal to r omega, right? Because I already know what r is. It was given to me in the diameter I know. And I just found angular speed w, so I can just use that r omega formula, r omega. Now, we know that the radius of my saw blade is going to be half of 7 1/4, right? So it's going to be half of 7 1/4, which ends up being, what, 3 1/8? Or 3.625? Yep, 625 inches. So now we can plug it into the formula, and I would have 3.625 inches times, I'm going to use the original omega of 10,400 pi radians per 1 minute. But the answer is supposed to be put in feet per minute, right? Isn't that what it says for me up there in the sentence, in the directions? That I need this to be in feet per minute? So I need to convert from inches into feet. So I would multiply by 1 foot over 12 inches. Inches are gone, leaving me in feet per minute. Now again, the radians, it doesn't, this label doesn't show up in my answer. It's just more of a, oh, I got it in the right spot. I've got my mode of my angle in the right form, okay? So I'm going to multiply straight across. 3.625 times 10,400 times pi and divide it by 12. And we get approximately 9869.8 feet per minute. Is that what you all get? Does that help?
Yes.
Okay. So when you're doing that Desmos activity, okay, pay attention to the labels. When you look at the blank where you're going to enter your answer, the label should be given to you in the blank, all right? It wasn't already given, it's probably not given to you in the body of the description. So just pay attention to what it is that you're trying to, how you have to answer the question, all right? Any questions on that? No questions?
Nope.
Okay, so you should be working on the homework for these sections.